Hello, my name is Raegan Brown, and this is my final project for Microprocessors Lab dealing with polling and interrupts. In lab, we have been discussing microcontrollers, specifically the MSP430G series, and how they use the methods of polling and using interrupts to service devices. This presentation will briefly describe and define the two methods, compare them, further explain interrupts and how they're implemented, and we'll conclude with a slight demonstration of interrupts using the MSP430. So when thinking of polling, we think of something constantly checking or polling something. In terms of embedded systems, polling refers to basically actively sampling the status of an external device by a client, program, a software to check for its readiness or its state. So this can be applied to software to any user interface where the microcontroller can poll buttons to verify if there are any user inputs. The external devices here are not independent systems. They basically depend on the microcontroller, and only the microcontroller can obtain access to the information that they need. So the process of this, to break it down basically, is the host will repeatedly check the busy bit of the controller until it becomes clear. When it's clear, the host will then write in the command register and write a byte into the data out register. The host will then set the command ready bit to 1, and when the controller senses the command ready bit is set, it will then set the busy bit. And then when the controller reads the command register, it senses that the write bit is set. It'll perform the necessary I/O operations on that device. Once that happens, the controller will then clear the command ready bit, and once it's completely executed, and then it'll clear the error bit to show successful operation and reset the busy bit back to 0. Some disadvantages of polling is that the CPU does not perform any useful work while waiting for the I/O device to become ready to transfer data. And you also have to wait and check whether new information has arrived, which wastes time. So to solve that problem of wasting time, we implement interrupts, and that's what we were working on in Lab 10. When you think of the word interrupt, you think of some sort of interrupting event that disrupts the normal execution of something and causes the execution of a special instruction. So in embedded systems, the interrupts are signals sent to the microcontroller to mark some sort of event that requires immediate attention. And interrupts, unlike polling, uses hardware to implement a more efficient way of letting the firmware know of any occurring events. The program that's associated with the interrupts is called the Interrupt Service Routine, or the ISR, also known as the interrupt handler. And we'll speak more on that in further in the presentation. The process for interrupts essentially is whenever a device needs some type of service, the device will notify the microcontroller by sending it an interrupt signal. Once the microcontroller receives this interrupt signal, it will request it to suspend its current execution and then jump to the ISR and execute that ISR subroutine. Once the ISR has completed implementing, it will resume at its last executed instruction in the main routine. So essentially, once the signal is called, it jumps to the ISR, and then once that's finished executing, it'll jump right back to where it left off in the main routine. So we can say that the interrupts are kind of like a telephone. We use the telephone analogy. Consider you have two situations. So you're at your house and you're expecting a call from someone very important. So anxious you are, you repeatedly and periodically grab the telephone every 5 seconds just to check if there's anyone on the line. But that means you would basically be wasting time, and you're not getting any productive work done while you're checking the phone. You're kind of polling the phone line without any success. Uh, on the other hand, you continue whatever you're doing, and when the telephone rings and receives an interrupt, you know to leave whatever you're doing and take care of that phone call. So you're servicing the telephone interrupt. That's how you can kind of, that's how uh, interrupts versus polling is. While you're polling, you're kind of wasting time continuously checking, but interrupts saves time in the fact that you're only servicing the device when you know that it needs it. So in an interrupt, we have our interrupt service routine, our ISR. It's similar to a normal subroutine that executes. However, it only executes when triggered by the reception of an interrupt signal. And this can also happen at unpredictable times. It also, once executed, must return to the main routine after execution in the spot where it left off. So that's kind of what's different between a normal subroutine and an ISR. Some important things to know what an ISR consists of is a pragma line, which is basically associated with the function of a particular interrupt vector, and we'll talk more about interrupt vectors in our next slide. And then we have an interrupt keyword, which happens at the beginning of the line that names the function that is going to be of the ISR. So here we have an example from Lab 10 of, just the definition of the interrupt vector using the pragma, and then using the keyword in interrupt keyword at the beginning of the function. To enable the interrupts in a program and set the global interrupt enable bit, the function call is called using this line of code here, enable interrupt. And that's how we are able to enable our interrupts. So interrupt vectors are basically like the memory locations of these ISRs. And they prioritize interrupts and save them in a queue if more than one interrupt is waiting to be handled. So just kind of think, they're used in the ISR for each, or they're used in the MSP430 or any microcontroller for each ISR, which has its own vector, and that's stored in what's called the vector table, which is located at the end of the program's memory. And as we can see over here, the MSP430 has predefined constants for their interrupt vectors, and these are them over here. There are also different types of interrupts. There are maskable interrupts and non-maskable interrupts. And maskable interrupts can be disabled by the individual enable and disable bit, as well as can be disabled by resetting the GIE bit in the SR. And then non-maskable interrupts, they're not masked by the GIE, and they're enabled by individual interrupt enabled bits. So now that we've kind of gone over this a little bit, it's time to put this to action. So I will now be showing you the implementation of an interrupt on our MSP430. Stay tuned. This will show our assembly code for our program that implements a interrupt. So to start, this is our bit vector that is for the pin port. JNECL3, that shows that we're going to be jumping to that corresponding label to perform our interrupt. But as you can take notice that we have the delay cycles 5,000, which means it'll take 5,000 nanoseconds before implementing this interrupt. So when the button is pressed, the interrupt will experience this sort of delay. And if it experiences an active low, if it's a negative, meaning the button has been pressed, then it will end up jumping to this CL3 condition where the current bit is going to be cleared. So what we have to, if the button is pressed, we jump to that CL3. Let's go find it. Here's the CL3, and the button will be it will be cleared. The interrupt will be cleared, and the controller will then resume to its main routine after being cleared. And this pretty much, this assembly code kind of really aligns with the C code. As we can see, P1IFG, it clears the interrupt using the 0 X00, and that's kind of the same over here in the C code. The command P1FG00 will clear the interrupt, which will then reset the interrupt after it's been called. And then when the interrupt is called, we'll wait for that delay. And if the button is then pressed, then the LED will toggle and flash. When it is not, then the interrupt will then clear again, and the controller will resume back to the main routine. So if we look at our microcontroller, as the debugger is as it's on, it will suspend all the interrupts. So if we go ahead and pause, our debugger, it should now light and make our debugger, make our controller flash, because it's allowing the interrupt to occur, which will signal the microcontroller to go ahead and flash the light. So overall, if we try to press the button in debug mode, the interrupt will not be able to work because it is suspended because of the breakpoint. However, if we pause the debugger, it will allow the interrupt to occur and the light to flash. Show what occurs in the registers. So these are some screenshots of the registers before and after the interrupts are implemented. So before the interrupts are implemented, we are going to have a clear interrupt flag, and the P1IFG shows that interrupt flag and how it's being cleared to 0, 0, 0. Right, and from looking at our previous lab, we know that we have defined LED to bit 6, the LED to bit 6, which is our pin 6 here, P6, and then our button to bit 3, and which is going to be here. So we want to take notice of these spots in the registers. Once we implement our enable, we see a change in these registers. So P1, the interrupt flag has now changed, and P6 is set to 1, and P3 is set to 1 as well. And that means that we know that the button has been pressed and the LED has reacted to it. So the button by bit 3 has been pressed, which is set to 1, and then the LED has reacted and it's lit, which is also 1. Once it is no longer pressed, we are going to expect for it to clear the interrupt so it can go back to its previous state, like back to the main routine. And so what we can see here is it is reset to clear, which is reset to 0. Our P6 is also reset to 0, and so is our P3, our button. And that's going to continue going on as long as the button is pressed. It's going to go through a change of changing the LED and the button bits to 1, and then clearing the interrupt flag and resetting them. And so that's basically how the microcontroller would show that in the registers. And with that being said, that is the conclusion of my presentation, and I hope you enjoyed this presentation on interrupts and polling using the MSP430.